So start off, I just will do some introductions, just two. My name's Ron Henderson. I'm the chairperson of physics and astronomy here at MTSU. I've been here for about 20 years, and this is Dr. Chuck Higgins. You can introduce yourself if you like.
Yep, I am one of the astronomers in the department, and I've been here for 17 years. So we're looking forward to talking to you about this amazing event that's coming up here. So he's going to start, and then I'll jump in later.
We're going to tag team. So it's not often that the physics and astronomy department gets this kind of attention. We're not used to it. I told the people with cameras in the room that a month ago I would have been a little nervous around cameras, but I've kind of gotten used to it. You know, it just happens. But I'll just tell you that I don't really have but one major goal today, and that's to kind of convey our big excitement for the eclipse to you. And then a second thing is, and I'm going to make these bolder on the website, but we have several sets of curriculum. There's a single sort of 6 through 12, but then there's a K through 6 that has a kindergarten 1 and a 2, 3 and a 4, 5, something like that. So it's broken down, and there are several days of curriculum at mtsu.edu/eclipse. So if you feel like doing something in your classroom, you don't have to write something from scratch. And also anything on this presentation is also going to be on that website, so you don't feel like you need to be making notes very much. Just sit back and enjoy it, kind of thing. So this is what the website looks like if you go there. It's slightly different now. We've added a frequently asked questions section. You can probably guess what the frequent questions are that we get with the department. Can I see the eclipse from my house? Do I need to have glasses? Those are absolutely the top two. Will you give me glasses? That's probably the next most common. That's become, about a quarter of my life is answering that question. Can I have glasses? And I can happily say to all of you, yes.
The question is, do you have glasses, right?
Well, they get them from their schools.
Have they arrived at your school that you know of?
August 15, okay. But
welcome, hi.
The school systems have them.
Yes.
They've been delivered. Yeah. So I thought I might just start off kind of motivating about why we care. So why are astronomers suddenly so excited about something that's happening outside? So how many of you that are here can remember having witnessed a total lunar eclipse? Is that maybe, kind of, sort of? If your hand's up, do you remember what you were looking at when you were outside, what it looked like? What kind of stuff do you remember about it?
You can see the shadow moving across the moon's surface.
Okay, so you're looking at the moon, and you're seeing something interesting happen with the moon. Okay, fair enough. What about what's coming up is a total solar eclipse. So have any of you experienced one of those, or do you have a memory of a solar eclipse?
Partial, yeah. Solar eclipse. I grew up in Texas.
Uh-huh.
And probably when I was in where my kids are in like 4th, 5th grade, I can remember going out with the glasses on the playground.
Okay.
And I couldn't tell you for sure if it was total solar eclipse, but I think it was close if it wasn't.
Okay, so what were you looking at when you went out?
The shadow. I mean, we saw it just like it comes over the shadow and the penumbra around it.
Okay, so you're looking at the sun is what I'm getting at. So in the lunar eclipse, you're looking at the moon. In the solar eclipse, you're looking at the sun. And so I want to talk a little bit about what's kind of going on there. Where I'm going to start, this looks really busy. Let me kind of first orient you to it and tell you why I think it's important. So in this photo, there's a single source of light. And can you tell it's on the left of the page? Right? So that's the sun. There's one sun on the left of the page. And there's a single Earth. So it's the blue thing in the middle. Everything else is the moon. And so it's the moon at different times of the month. And so what you see here is that during a month, all that really happens is that the moon goes around the Earth. It takes about 28 days for that to happen. And then the next month, the moon goes around the Earth. And so a question is, why do we see different phases of the moon as we go from day to day and week to week throughout the month? And that's sort of something I want to demo a little bit. And once you have a feeling for why we have lunar phases, that's a really good starting point for thinking about what's happening during different eclipses. And so what I'd like to do, I think this is the right number I poked a minute ago and I got dim but not dark, okay? And I'm going to use Dr. Higgins here to be the sun. And my basketball is going to be the moon. And so you all are going to be the earth. So all you have to do is sit there and be the earth. So one thing I'd like to point out, because go ahead and shine it, is that as the moon moves around from week to week, from day to day, does it make sense that how much of this earth, how much of this moon do you think is lit up at any given moment? So can you stay with me? Yeah. Does it make sense that no matter where I put it in this room, half the moon's going to get lit up all the time, right? And you can kind of see that also from this photo that as you look around 1, 2, 3, 4, 5, 6, 7, 8, every time you see a moon, it's half lit up. So because the moon's just a ball out there in the sky and the sun is shining on it, it's half lit up all the time. So what changes for the phase to go from one to another? So right now, and I'll kind of get closer to make it, maybe make it bright. Now, the entire lit up half of the moon is facing you, right? So do you know what phase we'd call this? It's the full moon. This is the brightest it will ever look. When the entire moon is lit, the entire portion of the moon that's facing you is lit up. Now, if I don't do anything except move, though, so sun, point at me, I will go halfway. Okay. So, can you imagine now, you know what, that's not working, right? We have to get together. Okay. So now, still, so what's happened is the sun looks like it's moved, but really the earth moved. And so now half of the moon is lit up. But from your perspective, how much of it is lit up? Okay, so quarter and a half are both good. If the full moon is full, then now it's about a half a moon. But we do call these quarter phases. And I don't think anyone knows why we go from full to quarter. I know some textbooks now will call them half moons and quarter moons or fulls and halves. But regardless, even though half of the moon is lit up, from your perspective, you only see the left part. You don't see the whole thing lit up. So nothing happened except the moon moved. You didn't move. And so you see a different phase. And so the point I'm getting at is that as the moon moves around the earth, the sun doesn't really change position. The earth changes position a little bit, but what's really happening is the moon's going around us and we see different phases. And so it goes from a full phase. It can also be a situation where you get to the point where the sun is here, you're still the earth, and the moon gets in between us. And now, how much of it is lit up? None of it's lit up. So obviously you all know that the back half of the moon that I'm looking at is lit up, but from your perspective, none of it is. So we go from a full phase where it's completely lit up to what we call a new phase just in a month, just because the moon moves. All right, so as we talk about eclipses, we've got 3 important things that we need to kind of consider. The sun, the earth, and the moon, and that's it. So the question is, what happens during an eclipse? An eclipse really just means that light from something is being blocked, right? Something is eclipsing the light from something else. We use eclipse in the vernacular if, one actor can eclipse another if the light on them is kind of, being dimmed, if you're getting some of the attention. In this case, an eclipse means something's going to block the light of the sun from reaching something else. So there's 2 possibilities. One possibility is the earth blocks some light from reaching the moon. And when that happens, we call it a lunar eclipse. And so the geometry has to be sun, earth, moon, in order for the earth to do some light blocking. Does that make sense? And so kind of in this picture, you've got a big sun, you've got the earth, and then the moon's on the other side, and you can see obviously the sun, the earth rather, is going to create a shadow. So when the moon passes in that shadow created by the earth, we call that a lunar eclipse. And so what's the other geometry we could have would be sun, moon, earth. And so now The moon has just moved around to a different phase. In this case, it's in what we would call the new phase, because if you imagine you're at Earth, the lit up side of the moon is opposite you. You can't see it. So this is in the new phase, is where it has to be in order for the moon to block some of the light from reaching the Earth. Well, the moon's not the same size as the Earth, and so it's not going to block all the light from reaching the Earth. And so this is our geometry. You may know the answer to this, and the way I'd like to ask it is maybe get from the beginning, I'll just kind of get you to vote. And you may know when this has happened or you may not. But the last total solar eclipse in Tennessee happened in the past, obviously, because it was in the past. And I'll give you 4 options here about how long ago do you think it was. So I've got 65 million years, 20,000 years, 500 years, and 65. So think about it for a second. Okay, so how many 65 million year agos? So many votes I get. Okay, last chance. 20,000 years ago. No. 500 years ago. Y'all are an enlightened crowd. I think the news has started to hit us. And then 65 years ago. In fact, it has been about a little over 500 years. And so 500 years ago, we had Columbus had not quite landed in the Caribbean. Mona Lisa was not yet painted. Shakespeare had not written Romeo and Juliet. It was a really, really long time ago. And the next one is in about 500 years. And so this is just a photo. This is a Sonic, I think, because Sonic restaurants will always be here, and I believe that's what they're going to look like. The one in my hometown from when I was a kid is still there. It's like the only restaurant that's survived all the years. So for Middle Tennessee, in this region, it's been about 500 years, and it's going to be another 500 years. So we can pretty clearly state that, truthfully state, that this is a once-in-a-lifetime event. If you're going to stay in Middle Tennessee, this is your only shot to ever see a total solar eclipse. You could travel somewhere else, and we'll get to that. But if you're going to stay here, this is the only shot you have. So the average time between solar eclipses for any particular location on Earth is about 375 years, but it varies a lot. There are places on Earth that in one 18-month period can have 2 total solar eclipses. There are locations on Earth where it can be over 2,000 years. So just depending on where you live. Now, the one that had 18 months, it wouldn't happen periodically like that. The next one would be longer. But lots of variation between the length of time between total solar eclipses. The theoretical limit on how long one could last, I'm talking about totality, and we'll get into what that means when you're in the path and the shadow passes over you. It could last as long as 7.5 minutes. The longest this particular eclipse will last, the very center of the eclipse, east to west, happens to be in southern Kentucky. And it's going to last about 2.5 minutes. So 2.5 is the absolute maximum for this eclipse. In this region where we are, it'll be a little over 1 minute of totality. So we waited 500 years, and it's going to last for 2 minutes. So it's a pretty rare event. And yeah, that place that's the center left to right and up down of this eclipse is in Hopkinsville, Kentucky. So a really legitimate question is, why are they so rare? Why has it been 500 years? Why is it going to be 500 years till this happens again? So to kind of start with, and this is the only time I'm going to change on you. This was the moon. Now it's the Earth. It's the only time it's going to change. But it looks very similar to the moon a few minutes ago. But we're going to go to a new model. So I'm going to let this be my model Earth. And what I'd like to do is get some feedback from you about, if this is a model Earth, then what does a model moon look like? And I'm saying to the proper scale. So if this is a model Earth, I've got 3 options here for you. And just you can think about it. I've got a little silver ball. I have a plastic golf ball, and I have baseball. And one of these is about the right size. So I'll let you vote again. You can just raise your hands as you find ones you like. What about the baseball? Okay, a few likes. What about the golf ball? A few likes. What about the silver ball? Okay, some of you are just not voting. That's not fair. You're over 18. You should vote because you cannot complain about what the outcome of this talk is if you don't vote. And the winner is the baseball. You won't go and take the baseball. Yeah, we'll go. That's a good idea. We'll go back with lights. So, for an Earth that is basketball size, a baseball is just almost perfectly the right size to be the moon. But to get the scale right, we need one more thing, right? We need to get the right distance. So if that's how big the moon is, then how far apart do these 2 objects need to be? So let's do it this way. This way everyone has to participate. If you start with your hand like this, I want you to pull it down when the Earth gets the right distance away from the moon, okay? That way I'll know when everyone's finished. Okay. All right, so I don't see anybody happy yet. Yeah, you start here. And when you think you've got it, you can rest. All right? Okay, most people are left. Lost a few more. Lost a few, got a few stragglers. Still got a few hands. You want to move that way a little bit till we see if we can get all our hands down. Still got 2 or 3. Okay, now they're happy. This is not bad. I didn't mark it off, but I will. So, okay, you come here. This is the right scale distance between the 2 objects. A nice way to think about it is it's about 30 Earths. So if the Earth is this size, we need about 30 Earths to go that way. This is a little less than a foot, so I ended up needing to go in about 24 feet. So already we can kind of see why it might be a little difficult to get a shadow cast by the baseball to land on the basketball. So already it starts to make a little sense that maybe this doesn't happen all the time. Thanks. Chuck. Oh, let me ask you one more. I'll finish my scale. If this is how big the Earth is, then how big is the sun? And if I go increase in size to like car size, the sun's even bigger. In fact, the right sort of dimension is a basketball court. So if you have a basketball court in length and a basketball court in height, then that's about the size of the sun. And it should be located almost 2 miles away. So it's huge and really, really far away. The diameter of the sun's about 100 of the diameters of the basketball. And the distance between the sun and the Earth is about 100 suns. So it's enormous and very far away. All right, so I just want to show you 4 quick things about that kind of add up to why we have the rarity. So one is that as the moon goes around the Earth during the month and during the year, it doesn't stay in the same plane. So you might think, okay, the new phase is when the moon is between the Earth and the sun. So we should get an eclipse every month, every time we have a new phase. And that would be right, except that sometimes the moon is above the Earth, sometimes it's below it. So the shadow misses us because of this tilted orbit. So the moon doesn't orbit just right. But about every 6th new moon, about twice a year, it does line up so some type of a solar eclipse can happen, but not a total solar eclipse. They're a little more rare because that's the moon in its orbit throughout the year is sometimes a little bit closer to Earth and it's sometimes a little farther away. And so that affects how much of the sky it takes up. So I won't tell you, I have a joke about the size, but it takes like 2 minutes, so I'm not telling it. But maybe I'll tell it later. But if you were to kind of reach up with your fingers and see how much of this basketball, how much of the space in the sky does this basketball take up for you? What I mean is you're saying, okay, it's about this big, right? And so especially those in the front, about how much does it take? All right? If I move it close to you, does it get bigger? Right, same basketball, but it takes up more of the sky. So during the time of the year where the moon is closest to Earth, it takes up a little more of the sky. And when it's farthest from Earth, it takes a little bit less. It doesn't vary a lot. It's about a 14% difference. But when the moon is farthest from us, it doesn't take enough of the sky to block the whole sun out. So we need we need the moon to be at what we call perigee. That's when it's on the close end to the Earth. So first we have a new moon phase. Then it has to be about every 6 months. It lines up correctly. And then to be at perigee, that happens about twice every 3 years. So about every 18 months, there's a total solar eclipse somewhere on our planet. So another reason that you don't hear about them very often is that the shadow is not very big and it moves really fast. It doesn't last that long. So the diameter can vary, but it's going to be about 70 miles. It's going to be about 68 miles actually on average is how big that shadow is as it moves across the United States. And it's fast. It's going to be moving at more than twice the speed of sound. So you can imagine that if the shadow of the moon is moving really fast, that's what controls how long you see it, how long it takes the whole shadow of the moon to pass over your spot on Earth. So yes, that's another reason that they don't that they're kind of rare because of that. But here you can kind of see I'm putting the fast together and that very small diameter, and you see that blue stripe. That's how much of the Earth is going to experience a total solar eclipse. So if you don't live or travel to somewhere inside that blue stripe, you will not experience a total solar eclipse. And that blue stripe, one thing you notice, a whole lot of it is over ocean. There's so much water covering the Earth that lots of eclipses start and end in the ocean and they never hit land. So again, rarity. So it's quite unusual. It's been a long time since we've had a total solar eclipse that passes across such populated areas like the United States. So this really is a big deal, and you'll find lots of people are going to travel, I think, to try to be a part of that. So this particular stripe is way less than 1% of the Earth. It's about a 1/5% of the Earth. So just not that many people will get to experience it. Okay, so I'm going to sort of yield to Dr. Higgins here for a little bit. Well,
sorry, I lost that one.
okay.
So let's try a little hands-on activity based on what you just heard. So I'm going to hand you, we don't have enough for everybody, but we'll hand around a few meter sticks and you can share. And what we're going to do is build an Earth-Moon scale model. That'll be within a meter stick. I don't know how many of those balls do we have? I think there's enough for 5.
I have 5 for those.
Okay.
1, 2,
Give you guys one over
3.
here.
I've got at least 5 balls. So we're okay
I'm
on.
gonna
Yeah, we're okay.
try to avoid
On supplies.
pitfalls here. So 1, 2, 3. I'll give one back here. We've got toothpicks and paper clips to clip the, you get toothpicks for
Well,
everybody? Yeah.
Well, I'll go behind you.
Okay, so
So
we've
everybody's got a stick, needs 2 paper clips.
2 clips. This is the earth.
Oh, you already have an earth.
Oh, yeah, you gave me one. 2 clips.
Your clips will be coming. You hand
2
one
clips.
back. You're mine. This is not something I can throw.
We didn't coordinate this part very well, did we?
And there's another one back behind them as well.
2 clips and 2 clips. And
Last piece.
we got Play-Doh and more toothpicks.
So the deal with the Play-Doh is, because that's your Earth, the Earth is about 4 times the diameter of the moon. So your Play-Doh moon needs to be about 1/4
So
of the size of
you
your
make
Earth.
a moon
So well, here, I'll just give you a big
the
blob
proper scale
and try to make it.
with the Play-Doh and stick it on
So this is
the
probably too
toothpick
much.
and then you separate the two to the
Okay,
proper
I'm gonna
distance.
hand you 2 to, if you don't mind, to pass back.
Yeah. Plenty of Play-Doh there, okay. Toothpicks, yes. So I moved it so it's not right. I
Right.
wanted him to,
Is that big enough?
yeah,
Make it a little bigger.
what she had was right.
Is that right?
So roll up your Play-Doh into the proper size and then clip it to the meter stick. So clip the earth at the 0 mark.
Or at 3. That way, you can't really get 0.
Right, or the 1 centimeter mark or something. And then clip the other toothpick with your moon the proper distance. Measure the width of the earth. What's the diameter, roughly? About an inch or,
Yeah, I think an inch is good.
oh, yeah, that's right. We're not on the metric system here. So I think it's yeah, so the ball is about an inch in diameter, the earth.
Tell me where to put this again. On the benchmark.
Or yeah, close to one end. And it's 1 inch. And therefore the moon, your Play-Doh moon would be how big? In inches. 1/4 inch. And how far away? 30 Earths. So 30 inches. So it'll fit nicely on the meter stick or yardstick. So clip it to the right place. And you can pass it around to some of those who didn't make one. But before you pass it, I want you to try something. So I want you to hold it with the moon close to your eye and Earth away from you. And I want you to try to line it up such that the moon is covering Earth from your point of view, right? You're lining it up such that the moon is just covering up the Earth. And just tilt it a little bit, this much. 5 degrees of angle doesn't seem like a lot, does it? But when on this scale, if you tip it just a nudge, the shadow of the moon does not hit the Earth. It misses it. And so what Ron was saying is that the precision of this thing is so tightly confined that you've got to have the moon and the sun and the Earth in the same plane. And then again, the phasing has to be right, the distance has to be right, otherwise you don't get an eclipse. So that's the right scale, and then you can see either way. You could do a lunar eclipse and do it this way, right? So you don't get a lunar eclipse every month either, do you? Same thing, the Earth's shadow misses the moon each month because they don't line up. So that's a very simple and a neat scale that you can do with your students. Okay. Got the clicker? Yeah. All right, I'm going to talk a little bit about what you're going to see, what you're going to experience. First thing is I'm going to help you win your next Scrabble game. And you can use this word and score big, big points. Syzygy. Syzygy. So it's an alignment of three objects. And it doesn't necessarily mean, in particular, doesn't have to deal with astronomy, but in this case it does. So when you have three bodies in alignment, that's a syzygy. So when you have a solar eclipse or a lunar eclipse, that is, by definition, a syzygy. And this just shows you how the plane of the moon and the Earth and the sun do not line up here, but they do line up here and 6 months later. But as he mentioned, not only do you have to be either the moon has to be, the Earth has to be in those two places, but the moon has to be in the right phase and the right distance. And that shadow has to hit your location. And that changes in longitude and latitude. So that it makes it even more rare. And this illustrates how we can predict these eclipses. They happen in cycles. And one major cycle is called the Saros cycle. It's an 18-year cycle of the sun. And the image here shows you the path of the lunar shadow for the last 24 years. And what I want to highlight for you is every 18 years you get a similar alignment. But notice there in 99 and then the one in 2017, notice how the shadows have the same kind of arch shape. So 18 years apart. But longitude has shifted, right? One happened in Europe, and now we're going to get one. So you don't get an eclipse every 18 years in your location. So would you get one 3 times that? Well, there is a 54-year cycle as well. And here's a couple of other similar shadow paths that are 18 years apart. So that's shifted in longitude. Of course, the Earth is rotating. And then a third one here. So 18 years apart, you get similar shadow paths. But on average, as Ron said, it's almost 400 years till you get one in your particular location. And he mentioned this before, but here's the shadow path. If you are not inside the 70-mile wide dark shadow, that's the umbral shadow, you will see a partial eclipse. And notice how wide the partial eclipse zone is. All of North America, Central America, and the northern part of South America will see a partial solar eclipse. So many, many, many more people see a partial eclipse than do a total solar. I've only seen one total solar eclipse, and I got clouded out. So I'm not counting it. Yeah, so I'm with you. This is going to be new to me as well. So from start on land, so when the shadow hits Oregon till it leaves South Carolina, it takes about 90 minutes. And NASA has got stations all along this path, so they're going to be able to track and take pictures of this thing for the whole time. And when you zoom in on Tennessee, you get an idea of where the eclipse shadow path is and where it is not. So if you live in Christiana, you are not going to get totality. You are going to get, a 95% or 96%, 97% total partial eclipse. which is really interesting, by the way. But I want you to move. I want you to travel that extra 10 miles or whatever it is to get in the path of totality, if possible, because it's that interesting. It's that unique. Yeah, John?
We have actually schools coming up in Alabama.
Yeah, so MTSU, we have our observing event. We have people from Northern Alabama that are going to be here. And you are welcome as well to come. I know some of you will be here. But again, look at the entire city of Franklin, Spring Hill. They are not in the path of totality. So from about Murfreesboro up to Bowling Green, that's the width. And a sea of humanity will be moving to this 70-mile wide path on the 20th and 21st. It's going to get quite crazy, I'm sure. But here we are. We're on the edge of totality. So we only get 1 minute and 5 seconds of totality. And when you're close to the center line, that's where you'll get almost 2 minutes and 40 seconds. But as long as you're in that zone, you will experience the awesomeness that will be a total solar eclipse. Here we are. We're well inside the edge there. So if you're sort of above I-24, north and east of I-24, you're fine. So what are you going to experience on that day? What we're going to plan is at 11 a.m., that's when we're kind of officially opening our campus event. And we will have telescopes set up. We will have eclipse glasses here for people who come. And we will have myself and other astronomers here to answer questions. We've got a stage. We're going to have live music for an hour and a half. And then we'll have a program talking about the eclipse and prepping people to what they should do before, during, and after totality. So about 12 o'clock, that's when the moon just starts to cover the sun. We call that first contact. And over the next almost an hour and a half, you will get a very slow progression of partial eclipse phases. So there's plenty of time to look. There's plenty of time to put your glasses on, look at the partial phases, and then go and do something else. Look through a telescope. You don't have to rush and look at the telescope right away. You've got an hour and a half before and then an hour and a half after. And that we call last contact. So the entire event is a 3-hour event. But totality is very, very short. 1 to maybe 2 minutes and 40 seconds at most. So we're expecting a huge crowd here, and we're excited about it. It's going to be a lot of fun. And we'll be here until the last contact. What is a total solar eclipse like? So I've been reading a lot and talked to people who have been in solar eclipses. Here you see a beautiful montage of images of partial phases and then the total phase. First thing is, the first hour or so, you won't notice the difference of light. The sun is incredibly bright, and not until the moon covers almost 90% of the sun will you even notice that, oh, it's starting to get a little dim out here. So about 20 minutes or so prior to totality, you'll start to feel that it's getting a little bit twilight-like, and then it'll get darker and darker and darker. You might notice, if you're in a quiet place, you might notice animals doing strange things at what they do at twilight. Birds will go to roost. Cicadas might start chirping, and crickets might chirping, but during totality, everybody knows that something weird's happening, and then they'll get quiet. So if you're not amongst the 10,000 or so we're expecting here, you might actually notice those sounds. Twilight at 90%, just before totality, and then just after totality, you might notice a really fun and interesting visual experience. And you can see it on the screen there. The moon is not perfectly round. It's got mountains and valleys on it. And so right before totality, some of that sunlight will kind of pierce through the valleys on the edge of the moon. And you'll see little beads of light just on the edge of the lunar surface right before totality. And that's called Bailey's beads. And then you might see the last flash of light before totality. It's one bright blob of light. And then you see the ring of light around the sun just before totality on the other side. That's called the diamond ring effect. So look for that. And then totality, right? You get darkness. And it's happening at 1:30 in the afternoon. So the sun is very high in the sky. Of course, it's going to be hot and mid-August. But it might get 10 degrees cooler because you're in the shade, essentially. So you'll feel a changing temperature. I have heard that there might be a slight breeze, kind of a gentle wind that you might feel during totality. It will not get pitch black because you see the crown, the ring of light around the sun called the corona, the crown. And that is the upper atmosphere of the sun that's so thin and so dim we don't see it normally. The sun is too bright. But during an eclipse, that will show up as this beautiful halo of light around the sun, and that will cause enough light so it will resemble what you might experience if you're out during a full moon. So it's dark, but not pitch black. Street lights might come on. I'm not sure how they're timed, but you might see that. You don't want to be underneath a street light when you're looking. So if you are, just move away from it, and then you'll get to see those beautiful patterns and shapes around the sun. So you'll notice the temperature changing, the pattern of light changes. It's amazing that event, or this event that's going to happen, is going to be quite memorable. So all of you have remembered when you saw your first partial eclipse. Your kids will as well. They will remember this for the rest of their life, and so will you. It's that rare, important, and incredible. John, you got a comment?
About the darkness. The darkness is about the light we'll see from the full moon. So the equivalent would be turning the room lights off and just having them glowing. So it's going to be dark. Okay, it's not going to be easy to walk around. Street lights are going to come on, and it's going to be dark enough that you're not going to want to be running around.
Yeah, and it changes fast, right? I mean, it's a very quick process. So it goes from light to full moon darkness very quickly. So, it takes your eyes time to adjust to that. So you do not want to be, as he said, you don't be running around doing something. You'll trip over something if you're not careful. Here's some pictures of the partial phases and the diamond ring and the Bailey's beads that you can see. So you can look for those when you're looking at the sun with your solar glasses on. The picture in the upper right is the corona, and sometimes you'll see streamers coming out of the sun. The corona changes every solar eclipse because the magnetic field on the sun is constantly changing. And so that's evidence of the solar magnetic field. You will see stars during the day and planets. So this is a simulation of what you will see from Murfreesboro, Tennessee, August 21st 1:29 in the afternoon, looking south. Do you see a sun? It's gone. You will see a hole in the sky. It will look like somebody cut a hole in the sky. And you will see two bright objects. To the right, it'll be the brightest one. That's Venus. And then to the left is Jupiter. And then many of the stars. So Mercury, Mars, they're going to be very tough to see because they're close to the sun and the corona. It'd be hard to see them. There's a bright star Regulus right next to the moon and the sun there. You might see that, but that's going to be kind of tough. But you will definitely see Venus, Jupiter, and maybe a couple of these other bright stars. And these are winter stars. These are stars you normally see at night in the wintertime. They're out there. We just don't see them during the daytime. But you will on August 21st. So that's memorable, that you will see stars during the day. Oh, this shows you the plane of the Earth-Sun, called the ecliptic plane. And notice how the planets all lie in that plane. Not exactly, but all pretty close to the plane of the Earth-Sun. Here is the lunar eclipse shadow, the umbral and penumbral shadow from space. That's kind of a neat image. And another montage image there, a time-lapse image. And then the one in the center is what we call an annular eclipse. So this is what Ron was talking about earlier, when the sun is the moon is a little bit too far away, therefore its angular size gets a little smaller, and therefore it will not cover up the entire face of the sun. So you get a ring, an annulus of light, but it's not nearly as cool as a total solar eclipse. So, but that's what an annular eclipse looks like. Have you ever seen the dark side of the moon? You see parts of it during quarter phase, first quarter, third quarter. You see part of the dark side of the moon. Here, you're seeing all of the dark side of the moon. Now, it's the same side we see during the lighted side, because remember, the same side of the moon always faces the Earth. But here, during totality, you're actually looking at the dark side of the moon. And this image is an absolute one of the best images of a total solar eclipse ever taken. It's a conglomerate of 55 images under near perfect sky conditions in Mongolia. And you can see, look at the streamers, look at the, I don't remember which planet that is to the left. I want to say Venus, but I'm not sure. And then you've got a star cluster over there. Just beautiful, beautiful image. And there'll be lots of those, of course, in a couple of weeks. This is going to be the most viewed, most filmed, most observed eclipse of all time up to this point, because of the location that it's hitting the central U.S. And so many people have access to the path of totality. So let me play you, just to give you a little bit of an experience of what it might be like, let me play you this video. Let me dim the lights a little bit. Here, and let's see if I can do this. That's a diamond ring. That's just a little taste. You can find, lots of videos out there, longer. But you get the excitement that's going to happen. At totality, people will start screaming. People might start crying. I'm kidding you not. This is this is a very emotional experience for a lot of people. It's so rare. People are so excited. It's just so different than anything you'll ever experience. That's why I'm begging you, if you're not in Murfreesboro, if you're south of I-24, try to get up here. I know you've got classes and kids. I'm just begging you to do it because it's an experience. They're gonna remember it anyway, but this is something that's just that much better. People will go nuts, and in a good way. I mean, it is that much fun, that much excitement, and it's such an incredible teaching and learning experience. Like, we're trying to get you a little bit of background information about the lunar phases and why this is so rare and what's happening, and let's create some scientists. Let's create some engineers. Let's find the next astronaut in your classrooms. That this experience might be the push to make that happen. That's what's so much fun about having this right in our backyard. Let's see. There's a list. These are on the website. So there's a few more really nice videos that you can get on YouTube. And there will be some science done. Let's not gloss over that. So NASA has professionals and amateurs looking at the eclipse all along the path. So they're going to be watching this. Essentially, they're going to get 90 minutes of totality. They're going to see how the solar corona changes, and they can study that magnetic field over a 90-minute period. I personally am involved with a NASA project. I will be using radio telescopes to measure whether the solar eclipse, how that affects the Earth's ionosphere, the charged particle atmosphere. So when the lunar shadow hits the upper atmosphere, that's going to change like it changes when it goes from day to night. So I'm actually going to be studying that, and a team of scientists around the country are going to be looking at that as well. So we have some science going on here. The most famous science experiment dealing with a solar eclipse was 1919. So 4 years after Einstein put forth his theory of general relativity, 1915, scientists realized that they could test the theory. And the theory suggests that massive objects curve space-time. So the light traveling through space, if it comes close to a massive object like a star, the path of light will get bent. So very clever. What they do is they take a picture of the sky, and the stars are so far away, they're fixed in space, right? They don't move. I mean, they do, but so tiny, the amount is so tiny, we don't notice it for thousands of years. So they take a picture of the sky without the sun there, and then they take a picture of the sky during the total solar eclipse, so they know where the star should be without the sun there, and then they take a picture and measure where the star's location is during the solar eclipse, and they found that the star was shifted in its position almost exactly what Einstein predicted. So 1919 was really a confirmation of the theory of general relativity. It's amazing. So I'm going to leave you with just a few tips about safety. So we've got some videos up on the website for you to look at, but just briefly, there's 4 good ways to view the eclipse. The best way is use your glasses, right? So you need your glasses on during all partial phases, before and after, before and after totality. You want to make sure you're wearing your glasses. And during totality, take them off. You won't see anything otherwise. The glasses are so dark, the only thing you can see is the sun. So when the sun disappears, so does everything else. So you must take your glasses off during that 1 minute and look at the sun directly. That's the only time you can do so. And then glasses back on 1 minute later. And you'll see it start to, the sunlight, blob of light will come out again, and then you put your glasses back on. So that's the simplest way. If you've got telescopes or binoculars, you need the solar filters. Absolutely. That's where you really risk hurting yourself, is if you happen to look through some binoculars or some other optical device without a special filter, a camera even. Don't do it. Not until totality, because you will ruin your electronics or ruin your eyes. Either way. You can do a pinhole camera. That's an easy and a fun way to do with your students. Let's do the light. Get you to shine the light. Here. The best way, you can get a 3x5 card and punch a hole in it, or take a piece of cardboard and cover it with aluminum foil, and then poke a hole in the aluminum foil, and then all you're doing, let's see if I can get it this way, all you're doing is, well, let's see, projecting the light onto another 3x5 card or a white sheet of paper. So that's not showing up terribly well here, but yeah, you can kind of see it there. But you will get, that's a great way to view the partial phases. You'll see the bite out of the cookie or whatever, so it's really fun to kind of track that over time. So that's a real easy and simple thing you can do while you're outside waiting. If you have welder's goggles, then you can use them, but they have to be number 14 or darker. So don't go and buy, oh, this is welding glass, I can use it. That's a mistake. I mean, you'll damage your eyes. The other thing that I encourage you to try is stand under a tree. So the trees themselves become pinhole cameras, the leaves. And so you will see hundreds or thousands of partial solar eclipses on the ground. So that's a really neat experience. So I can't emphasize enough, when you're looking at the sun anytime, before or after totality, you need the glasses or solar filters of some kind. During totality, you can look directly at the sun. And you should tell your students that. It's fine. That's the only time. They got 1 minute if they're in the path of totality. If you're in Christiana, you cannot take your glasses off. It will get dimmer, but it won't get dark. You won't get that darkness of totality. So it's a very simple thing. We all have a mechanism of protecting ourselves. We're not going to stare at the sun without protection. It hurts. It will hurt your students and your children. So they won't do it. So you should, if they're really young, obviously you want to supervise, but it's not that big of a worry, because people will protect themselves. But the simple way to say it is glasses on anytime you can see light coming from the sun, and then 1 minute of totality, you can take your glasses off.
Does some of the concern come from pupil dilation, because it's a little bit different than full bright sun, your pupils are closing, but during maybe the darkest part of partial, your pupils start to open up a little bit? Is that?
Well, that's right. So yeah, as darkness gets increases, yeah, your pupils are dilating a little bit. So that's true. You're letting more light in, and that if you're looking through something at the sun, that's going to have more chance to hurt your eyes. So you just don't want to do that, obviously. Any other questions about eclipses in general, or frequency, or the science, anything? John?
When you're looking for the eclipse glasses, and you can't see anything more, it's certainly safe to put them down. And as soon as you see the light, it's going to need to focus. So
yeah, I mean that's a good way. Is as soon as you cannot see something through your glasses, then you can take them off. And as soon as that light comes back on, then you'll put your glasses back on. We have a star party tomorrow night. We're doing how to photograph solar eclipses. So Dr. John Wallen up here is going to be talking at 7:30. It's in the LRC building across from the new science building if you want to come to that. It's open to the public. And then on the 20th, on Sunday afternoon, we've got a panel. We've got a few scientists visiting us from NASA and other institutions, and we'll be holding a discussion panel. 3 o'clock in the afternoon in New Science Building. If you want to come to that, you're welcome to do that as well. And of course, you're welcome here on August 21st. So we hope to see many of you and maybe some of your students too. Anything else you
Except
have?
going outside.
Yeah. Is it the sun up? Have you checked?
I am checked.
Well, let's go. If there's no
Let me
questions,
check.
let's go take a look at the sun with solar glasses. We want you to see it.